Welcome to Quantum Innovations in Space with CARIOQA, the podcast where we explore the fascinating world of quantum technologies and their impact on space exploration. Brought to you by the CARIOQA PMP Project, this series delves into how quantum sensors are revolutionizing gravity measurement, space navigation, and Earth observation. In each episode, we bring you insights from top scientists, engineers, and innovators working on the cutting edge of quantum research. Whether you're a space enthusiast or just curious about the future of science, you're in the right place. Today, we'll take a step back and look at something fundamental, gravity itself. Why do we measure it from space? How? And what are the missions that made it possible? To walk us through this topic, I am joined by Félix Perosanz, Head of Earth Observation Solid Space Programs at CNES, the French space agency, which is also coordinating the CARIOQA PMP project. Félix, pleasure to have you today. Hi.
Hi, Nina. Nice to see you.
Yeah. Well, let's begin with the very foundation, gravity. We all experience it every day, of course, but what is it really?
Well, yes, you're right. We are all submitted to gravity, and I guess everybody knows the story of Newton and the apple. The apple comes off the tree and free falls to the ground. And the reason the apple falls is the force called gravity, which is generated by the mass of the Earth. And this force depends on the mass of the Earth and the distance to the Earth. Just to give you an example, on the moon, for example, the gravity force is 5 times smaller on the moon than on the Earth. And again, if you move away from the Earth using a plane, for example, the gravity will decrease. So the closer you are to the Earth, the higher is the gravity. And this gravity depends on it doesn't depend, this is an interesting thing to know, it doesn't depend on the mass of the apple. For example, if we come back to the apple falling, whatever the mass of the apple, it can be a big or small apple, the free fall, the acceleration of the apple will be the same. Okay? So it can even be a bird feather or cannonball or a rock or whatever, the acceleration will be the same. Well, if you do yourself the experiment, you will not see this. And the reason is because on the Earth, we have the atmosphere, as you know. I mean, lucky. So for us, because we couldn't breathe if we wouldn't have the atmosphere. So we have the atmosphere, which is great for us. But this atmosphere generates an additional force. In addition to gravity, we have an additional force. We call it the atmospheric drag. Okay. This atmospheric drag generates an additional force, and when the bird feather falls and the cannonball falls, you have a different trajectory, but this is because of the atmosphere, not because of the gravity.
Okay.
And in vacuum conditions, for example, if you pump all the air, then you would see exactly the same trajectory from a bird feather and a cannonball. And you have on the web very nice videos showing this. So I recommend to have a look to those videos on the internet. And you will see how, again, a bird feather and a cannonball fall exactly at the same velocity because they are submitted to the same gravitational force, which produces an acceleration and the same trajectory.
Okay. Well, that makes sense. I think it was a good introduction to the topic of the day. So now that we have a bit more of an idea and a bit more of an understanding of what gravity is, how do we actually go and measure it?
Well, the instrument we use is called a gravimeter. It sounds logical. So the question is how a gravimeter works. If we come back again to the apple or the proof, I will call it the proof mass because this is a technical word we use in physics. So the gravity forces produces an acceleration of the proof mass. And the idea of a gravimeter is to measure how this proof mass falls. So a gravimeter looks like a tube or a kind of box, if you wish, in which you pump all the air just to be sure you are in vacuum conditions. There is no air anymore inside the box. And you have a proof mass inside and you just make it falling and you measure the falling time of the proof mass. And this is how we measure gravity on the Earth using a gravimeter.
Okay. So now we have the what, we have the how. Now is the why, because I understand the how, but why does it matter to measure gravity at all, and what can it reveal about our planet?
Yeah, in fact, this is a very important physical parameter to measure, because this gravitational attraction of the Earth locally depends on the mass distribution of the Earth. In other words, on the local density of the Earth. So if you move to a different location where the density inside the Earth is different, or if you get closer to a mountain, for example, then the gravity will change. So with your gravimeter, moving from one point to another one, you will measure different things, and these things, a different signal, and this signal, the intensity of the gravity will reflect the mass distribution of the Earth. So the shape of the Earth and the density of what is inside the Earth. And there's a lot of complexity in this shape and in this mass distribution. And this helps a lot in understanding the Earth system, how it behaves also.
Okay. So when you talk about the different density, it can be mountains, oceans, this kind of different things, right?
Exactly. If it's oil, if it's gold, if it's,
Yes,
you see how important it can be to detect this kind of minerals inside the Earth. And we use gravimeters to sense the underground. And this is the only way. Using images, for example, images doesn't make images of what you have inside the Earth.
No.
So gravimeter and gravimetry is almost the only technique to know what we have underground.
Okay. Well, all of that brings us to a bigger question. Why go to space at all? Why measuring gravity from space is often more effective than doing it here on the ground?
Yeah. Well, in fact, if you want to have a global view of the Earth of its gravity field, you could use a gravimeter, but in this case, you would have to cover the entire planet and cover all the continents, including polar areas, going to the top of the mountains, and so and even go on the oceans, and it would be, of course, very complicated, very difficult, and nobody even tried to do that.
Yeah.
So while a satellite turns around the Earth, while the Earth is turning around its rotation axis. So using a satellite, you can have a global map of the Earth. A satellite, while is in its orbit, is, of course, submitted to gravity. A satellite in its orbit is free falling, like a proof mass, like the apple on the Earth. The satellite is free falling in the gravitational field of the Earth. So this is the same principle as a gravimeter on the ground, except that the time of free falling is infinite, continuous. It can be years instead of milliseconds in a gravimeter on the ground. So the satellite is free falling. It's a kind of perfect proof mass to measure the gravity of the Earth. And in addition, it gives you a global map of the Earth. So by observing the trajectory of that proof mass, of the satellite itself, you have access to the gravity of the Earth, and you can make a global map. This is the good news, the good thing from using satellite.
Okay, well, that makes sense, and that make indeed a huge difference between measuring it from the ground and from space. I understand that. Now, if we talk a bit about space missions, there are many space missions, such as CHAMP, GRACE, and GHOST, for example. But can you tell us a bit more about what made them so significant and why it took until the 2000s to launch them?
Yeah, it's a good question, because since the beginning of the space age, as I was mentioning, as a satellite is a proof mass to measure gravity, since the very first satellites, we use satellites to measure the gravity of the Earth. However, the accuracy we were able to get from those satellites was not good enough to really understand the Earth system and to answer all the questions the scientists were asking. So we were really needed dedicated missions, but we had some limitations. And I will come back to this, but these dedicated missions, as you mentioned, finally happened in 2000 with the CHAMP mission. Then came the GRACE mission in 2002, and then the GHOST mission in 2009, and we got a very great improvement for those missions. Why did we have to wait until the 2000 to launch these missions? Because if you want to measure precisely the gravity of the Earth, you need to be close to the Earth. The reason is what I was mentioning in the introduction, is because the intensity of the gravitational attraction depends on the distance to the Earth. The closer you are, the higher is the intensity. So if you want to make a precise measurement, you need to be close. And close means, for a satellite, to be below 500 kilometers of altitude, which is very low compared to classical missions, I would say.
Okay.
But then, if you fly at 500 or even lower, at a lower altitude, you have two problems. The first one is, again, the atmosphere. Like on the ground, the satellite will have some residuals of the atmosphere, even at 500 or 400 kilometers, and this atmosphere will produce a drag force on the satellite. So the satellite is not really free falling, but you have an additional force, which is the drag, or atmospheric drag acting on the satellite. So you will have to separate the two effects if you want to measure gravity.
Okay.
And so to measure this atmospheric drag, we need an additional instrument, which is called an accelerometer. And this accelerometer will be able to measure all these non-gravitational forces acting on the satellite. And will help to separate the gravitational part to the non-gravitational part. But the second problem we have when we fly at a very low altitude is to be able to track the satellite, because we need to know the trajectory of the satellite. This is what gives the gravitational attraction. Okay, you need the trajectory of the satellite, like the trajectory of the proof mass inside the gravimeter. We need to know the trajectory of the free fall of the satellite in space, and for that, to track a satellite, the usual way is to use a ground network of stations. But at 400 or 500 kilometers, the altitude is so low that we would need a very, very dense network of stations that we don't have. And we would need even stations on the oceans, and we don't have this.
Okay. Yeah.
So we have a very strong limitation, and the only solution we had for this problem was to use, instead of a global network of stations on the ground, to use a global network of satellites.
All right.
Like the GPS system, you all know. So GPS satellites are used to track satellites that need to be tracked at very low very low altitude. So both accelerometers and both the GPS system were available only in the late 90s, I would say. So we had to wait 2000 before being able to launch this CHAMP mission. That was the very first mission dedicated to high accuracy gravity field model determination.
So we mentioned CHAMP, but there were also GRACE and GOES as significant missions. Of course, there are many others, but if we focus on those three, I believe they all had different strategies. Can you tell us a bit more how they varied from each other?
Yeah, sure. So if we come back to CHAMP, the idea is the satellite is a proof mass. It's tracked by GPS continuously, so we have its trajectory. We have a precise accelerometer on board to, let's say, separate the signal coming from the atmospheric drag. So what remains is the gravity. So we can directly observe the gravity from the trajectory of CHAMP.
Okay.
So sounds simple, but again,
almost
from a technological point of view, of course, this is something that needed a lot of developments and including a very precise accelerometer, which is something of very high technology. But at the end, with only 1 month of CHAMP observations, we were able to do, scientists were able to produce a gravity field model, which precision was something like 10 times better than all the other missions before.
Okay, so that's impressive.
So it's really impressive, and this really was a big jump in understanding and mapping the gravity field of the Earth. And of course, there's a lot of science that became possible thanks to CHAMP. And then came the GRACE mission. You're right, just 2 years after that, and in this case. Instead of having one satellite, we have 2 satellites, and the 2 satellites are on the same orbit.
Okay.
They are only separated by something around 200 kilometers. Okay. And in this case, the 2 satellites are acting as proof masses. Okay. It is not only one, but the 2 satellites. So we are in fact observing the relative impact of the gravity field on the 2 proof masses, because in addition to accelerometers on board GRACE, like on CHAMP, we have an additional instrument which measures very precisely the distance between the 2 satellites. So just to illustrate what's happening, let's imagine the satellites are flying above the Alps mountains. Okay, so the first satellite flies over the Alps, and because of the mass of the Alps, and this anomaly, I would say, in the gravity field, the first satellite is accelerated.
Okay.
So the distance between the 2 satellites will change a little bit. Then the second satellite will come, and again, above the Alps, it will be accelerated. It will be accelerated, and the distance again will change. So by measuring precisely the distance between the 2 satellites, we have access to all these gravity anomalies on the Earth with a precision like 10 times better than with the CHAMP mission. So again, GRACE was a kind of revolution.
Yeah.
And in addition to this, the nice thing with GRACE mission is that because of the repetitivity, if you wish, of the mission, after 1 month of mission, we were able to have a very nice image, like an image. It's not an image, like a picture, but a nice map of the gravity of the Earth. So the next month, you could do it again and have a second image of the Earth, and then the month after another image. And since 2002, we have a kind of movie of the gravity of the Earth, which is changing. So with GRACE, we started being able to track the changes in the gravity of the Earth, because it's a complex shape, but this shape is also changing as a function of time, because the gravity of the Earth is changing as a function of time. Then came the GOES mission. And again, this is the same principle, but instead of measuring the difference of gravity between two proof masses, which are two satellites, we have two proof masses, but the two proof masses are inside the satellite.
Inside one satellite?
Inside one single satellite.
All right.
One single satellite. So, and to deal with the problem of the atmospheric drag, because GOES was flying at a very, very low altitude of about below 300 kilometers. So an altitude where the drag becomes very critical. There was a system called drag compensation inside the satellite. So we have an accelerometer on board the satellite. So, and a kind of engine, if you wish, thrusters. And from the measurement of the drag, the thrusters were compensating the drag, just to maintain the satellite really in a free fall condition. So the two proof masses inside the satellite were really in free fall condition, just gravity and the precision, because again, these two proof masses were only separated by half a meter. In this case, you measure the relative gravity of very small structures of the Earth's gravity. So we were able with GOES to access to very, very high resolution, spatial resolution of the gravity of the Earth, while the GOES mission with two proof masses at a distance of 200 kilometers provide information more at the continental level. So I would say that GOES and GRACE were very complementary missions in terms of spatial resolution of the gravitational field that can be observed.
And it's very interesting to hear, as you're speaking about the three different missions, how each of them built on the previous one to come to like a better level of granularity or better quality of results, So it's very interesting.
Exactly. Yeah, there's a kind of logic behind this. I can tell you it was a big effort of the international community to push those missions and make them real. It took years and years, but finally we got them, and
Amazing. Well, now if we're talking about mission, let's look ahead to the future. What is the scientific community asking for when it comes to upcoming and future gravity mission, and what are the biggest challenges?
Yeah, well, as we were saying, these missions, CHAMP, GRACE, GOES, were very successful, and they provide wonderful information for scientists. And anyway, measuring gravity from space is the only way, in fact, to have a global map of the mass redistribution of the Earth. I mean, the way the masses of the Earth moves from one place to the other one. For example, when Greenland is melting, so the mass of the ice which melts goes from Greenland to the ocean. So this is what we call mass redistribution. This kind of information, all this mass redistribution, is a very important input for scientists. So all these missions, measuring gravity from space is something which is needed. And the GRACE program, for example, has been continuing since 2002. And it's still active today. We are still measuring gravity with a mission called GRACE Follow-On. I mean, this is a continuity of GRACE. There's as I was saying, a very strong a need expressed by the scientific community asking for more precision and for higher temporal resolution. More precision to see more details. For example, if you have a drought phenomena somewhere, if you have a underwater somewhere, if you have a drought, if you have a mousson, I mean, small signals, they want to track those small signals. And instead of having an image of the gravity every month, they would like to have an image every 5 days, for example. Okay. And this is what we plan for the future. But there's quite a lot of challenges to overcome. Mm-hmm.
I believe so. Okay, so I believe that all of this brings us to CARIOQA, the space mission within which the CARIOQA PMP project is part of. Why would you say it is important to validate quantum accelerometers in orbit, and how does this mission fit into the future of gravity measurement from space?
Yeah, one of the key problem in the missions we have today, in terms of precision, comes from the instruments we have on board. And for example, on the GRACE and GRACE Follow-On missions, we, of course, have accelerometers, and you know why. But we are using what we call mechanical instruments. Okay. I mean, inside the accelerometer, we have a proof mass again. It is a mechanical proof mass. I mean, it's a piece of metal in an electrostatic chamber, and we are measuring the little displacement of this piece of metal. And you can imagine that, okay, you can improve such kind of instrument, but there's always a limitation when you use a mechanical instrument like this one. So there's a technological challenge to be able to provide accelerometers for the future missions that will not be based on mechanical techniques, but on another technique. And the alternative is to use quantum technology. So instead of, again, a physical piece of metal, using, for example, a cloud of atoms, and looking how this cloud of atoms falls due to gravity. This technology of quantum accelerometry, this is something that we start to master, to control on the ground. Mm-hmm. We have ground instruments, but this never flown on a satellite.
All right. Okay.
And this is something we really need to validate. And this is exactly the aim of the CARIOQA mission.
Yeah. Félix, thank you so much for walking us through the history and the future of gravity missions. It was a pleasure to discuss with you. I think it was really fascinating to see how something as universal as gravity is measured and used to understand our planet. In our next episode, we will dive into the instrument behind this technology, specifically how quantum sensors are being used for space-based gravimetry. You won't want to miss it. In the meantime, stay connected with CARIOQA PMP through our project and social media, and subscribe to the podcast so you don't miss an episode. Thanks for listening.